right, it is 1.5, infinite geometric series. Oh, sorry, I got some drawing here. Let's get rid of this. Okay, very good. By the way, if any of you find this background music for recording is rather annoying, please let me know. Meanwhile, I'm just going to keep trying this, and I'm not even too sure whether I feel more relaxed or more stressed, but hey, we will see. So infinite, we already defined what kind of sequence or series. It's either finite or infinite. Infinite means it goes forever, ever, never stops. Okay, so let's consider this is a very typical infinite series that goes forever, and also the R is just a half, right? So it's the next sequence, next term is always divided by half again, divided by half. So so these numbers eventually gets closer to each other, right? It gets closer because it just completely gets so small in the end. So that means, and the approach, this one, as a matter of fact, in the very end, approach a number. So then this kind of sequence is called the convergent, because it's converge to a real number. Now we can tell that because you cut into half forever, then supposedly the thing is nothing left. So this is approach to zero. So the way to say it is to say, well, this is basically starting point of calculus. So this is called this kind of sequence. When n is approach to infinity, and also here is a positive infinity, and the limit of this type of number approach to zero. So again, it says as n approaches an infinitely large number, or as n approaches positive infinity, the 1/2 to the power of n approaches zero. But now let's take a look at a very typical different, but almost like goes hand in hand type of thing, because this one R is 2. So you got a sequence that's 1 and then 2 and 4 and 8. So basically multiply, double it. And then this one, it does not converge to anywhere. It's, as a matter of fact, it goes into infinity. So then this is called the divergent. All right, so this type of thing is just a knowledge. And so in general, now pay attention to this one sentence here. So that means if the common ratio is smaller than 1 or larger than -1, also there's another way to write it, means that the absolute value of the R is smaller than 1, then the sequence will converge. But if the R absolute value is larger than 1, that means R is either larger than 1 or R is smaller than -1, and then the sequence will diverge. All right, so now let's take a look at the sum, the formula of the sum when the geometric sequence is infinite. So now we're starting from here. Okay, we start from here. So then if the R is, the absolute value of R is smaller than 1, that means this R, that when n approach to infinity, this one would approach to 0. So in this case, then this becomes 0. Therefore, the formula is this. So please note there are two conditions here. One condition is a sum now is infinite number of the terms add together, and also the common ratio, the absolute value of the common ratio is smaller than 1. Then the formula is that. Okay. Now take a look. This example you could study by yourself. Not a big deal. Okay. Now here it is trying to tell us how important this restriction is. Okay. So basically the way it's trying to prove to us that this restriction is important is, let's take a look at the sum. So if it's supposedly finite is well large enough the number add together. So then if the R is 1/2, means fall into this range, you add them together, you can pull the 1 out, and then you factor out a 1/2. Then you got the same sum here. So then you can rewrite it into, now this sum equals to 1 plus 1/2 sum. The reason why, as a matter of fact, you can write that way is because there's no ending. If there's an ending, you cannot pull out this one and still think this is the same as, if you understand what I mean. All right? And then in this case, well, then the sum become 2. You can imagine that because these ones all add together is close to being a 1, and there's a 1 here. Of course, 1 add 1, and it's equals to 2. That makes sense. But then this one, if you do the same manipulation, you leave this first term out and you factor out the 2 from the remaining terms, and you got these guys. It's the same as S. But then you got in the very end, you become the sum because -1. That doesn't make any sense whatsoever. You take a look at 1 plus 2 plus 4 plus 8. This is going on to infinity. How on earth you add them together using the same way to try to figure things out? Then you ended up with, you add them together, become -1. That is because this does not satisfy this restriction. Therefore, when they diverge, strange things do happen. All right. Now, again, we use the sigma notation to denote how we write it. So just take a look at this. That should be pretty straightforward. Okay. I think this example very similar to the example that I talked about in 1.4. So I think I can just skip this. I just wanted to keep the video as short as possible, and please take a look by yourself. Now this one is very similar than the dropping the ball, right? So very similar than dropping the ball, this. So this pendulum, so they basically goes this way, this way, this way, this way, right? So whenever they swing back, they lose certain momentum. And then they go back again, and then the distance becomes shorter. So what happens here is that here says each swing will lose 5%, right? So if you lose 5%, that means my second swing divided by my first swing, that is basically, it is 95%. So in this case, this R equals to 0.95. All right. So then we plug everything in. So at the beginning is 25. That's my first one. 1 minus this because this swing goes just about forever, and in the very end it stops. So we can just consider it as the infinite geometric series, and one can calculate the total distance for the pendulum that traveled. Okay, so now this one is very similar to the one that I demonstrated in 1.4. So please take a look at this, exactly the same. All right, okay, so what I find this example here is very interesting. So now let's take a look at this one. The repeating decimal, this is 0.2, repeating that. All right, so now note this way of writing out a decimal called expanded form. It is a very useful knowledge about how to write a decimal into a expanded fraction form. All right, so for example, 0.37, that is equals to 3 divided by 10 plus 7 divided by 100. That's exactly this. Okay, so now, so for this one, now we're using 0.2. The 2 does not repeat, only the 0.04, like the 4 not repeating. So this one repeating. So this one means 0.2444444, wow, goes forever. So now in this case, we're going to rewrite this, becomes 0.2 plus 0.04444. So in this case, 0.04 becomes 4 over 100. Then you got 0.004, then that is 4 over 1000. So this goes forever. So in this case, that means your R is 1 over 10. And your first term here, no, your first term is right here. The first term is here. And 1 minus R is that. And you calculate this, your answer is this. But this question, what I find is interesting is that I think in the past years you must have studied how to write a repeating decimal into a fraction. So if I go back to there, let's try how we do that. And it's going to be the same answer. So the way to do it, and this strategy, I always like this strategy about how to write a repeating decimal into a fraction. So therefore, repeating decimal is a rational number because it can be expressed into a fraction, right? So now let's see, what is this one here? So this, okay. So then I could say, well, why don't I let this become just x? So if I write this into a fraction form, what this x could be. So then in this case, I'm going to multiply both sides by, I can multiply both sides by 10, okay? So I'm going to say, okay, 10x now equals to 10 multiplied by 0.2 and 4 and 4 and 4 and 4, right? So that means 10x also equals to 2.4 and 4 and 4 and 4 and 4 forever going. And then right from the beginning, my x was equals to 0.2, 4 and 4 and 4 and 4. So now this time, I'm using this equation to subtract this equation. That means 10x minus x now equals to 2.4444, keep going, subtract 0.244444. So now if you do this one, that means 2.4444 subtract 0.24444. So you can realize these 4's are all canceled because of subtract. So then you got this 4 subtract 2 is 2. So you ended up 9x equals to 2.2. Okay, well now how much is our x? X equals to 2.2 divided by 9. Okay, this is not a fraction yet, but that's not a problem. If we multiply by 10, then that becomes x equals to 22 over 90. 22 over 90 divided by 2 on both sides. So that becomes 11. That becomes 45. Same answer. So x equals to 11 over 45. So the same answer as using infinite geometric theory to rewrite a repeating decimal into a fraction as a rational number. I personally like this kind of strategy better because I just find this is more interesting. I don't know. All right, but of course, so you do have exercise in the exercise set to do these rewriting repeating decimal into fraction practice. I would say either do this way or do this way. It will give you the same answer. You might even try both ways just to verify whether or not you're correct. All right, so the last example, I don't think this is very interesting, but hey, just for the sake of doing it. So this is the infinite geometric theory because this goes to infinity. All right. So then we know, but there's a restriction that x is only smaller than 45 degrees and larger than 0. So there's no negative degrees, or there's no anything larger than 45. So now r is the tangent x, because if you use the second term divided by first term, yes, give you this. And your first term will be 1 because k equals to 1, that becomes 0. Anything to the power of 0 is 1. And then when you approach infinity, then this is your sum, right? So this is your sum. So here is your sum. And the sum equals to 1. So then it turns out to be, if you just do 1 minus tangent, this one goes to there, equals to 1. That means tangent x equals to 0. But when tangent x equals to 0, either it's 0 degree or 180 degree. Reject this is because right from the beginning you have this restriction. Then it's done.